Hey guys, today we'll continue in our series where we go through the courses in FPGA Academy. Today we'll continue with Lab 2. Last time we finished part 4 and today we'll look at part 5 and part 6. If you haven't watched the previous parts, you can watch them on my YouTube channel. And we will continue with part 5. In part 4, you created VHDL code for a BCD adder. So that's what we have done in the previous parts. In the previous part, in part 4, we created adder, but we were not allowed to use if and else or case statements. A different approach for describing the, the adder in VHDL code is to specify an algorithm like the one represented by the following pseudocode. So this is exactly the same algorithm we have developed last time, but it's written pseudocode, and today we will do it in this way. It is reasonably straightforward to see what circuit could be used to implement this pseudocode. Line 1 and 9 represent adders. So these two lines are just adding numbers. Lines 2 to 8 correspond to multiplexers, and testing for the condition t is greater than 9 requires comparators. So here we need comparator, and if else is multiplexer. You are to write VHDL code that corresponds to this pseudocode. Know that you can perform addition operations in your VHDL code instead of subtraction shown in line 9. Here we can use addition. We can subtract two binary numbers, and we can use addition if we use two complement subtraction. So basically we take this number, we inverse it, we add 1, and then we can add these two numbers, and that will correspond to subtraction. The intent of this part of the exercise is to examine the effects of relying more on the VHDL compiler to design the circuit by using if-else statements along with the VHDL greater and plus operators. Perform the following steps. So last time we basically did comparator, we made multiplexer, we created adder, but this time we will rely more on the compiler to do these for us. So create a new Quartus project for your VHDL code. Use switches for the inputs and use switch 8 for the carry-in. The value of A should be displayed on the 7-segment display, while B should be on hex 3. So A and B are 4-bit binary numbers, and if you have 4-bit binary numbers, the maximum value is 15, but we are showing BCD numbers, and BCD numbers are just 0 through 9. So that's why we only need one 7-segment display, because we are only showing one digit. If we were to show 2 digits, we would need 2 7-segment displays. And we will basically create the same, we will use the same ports. So we'll use two binary numbers as inputs, and we also have our carry in here, and as output we will have some sum, and this sum will be represented as 2 BCD numbers. So for example, if you get 9 plus 4, that's 13. So S0 will be 3 and S1 will be 1. So that's what we are gonna do now. But before we begin, I would like to, this is entity prepared for today's exercise, but before we begin with part 5, I would like to simplify one thing that we have developed in the previous part. You can see that we have a lot of muxes here, and the only difference between them is that it's this one is 5-bit, so it takes as inputs 5-bit numbers. This one is 2-bit, this one is 1-bit. So the only difference between them is the length of the input. So what I would like to do is, I would like to simplify, and I will use generic for this. and I'll show you how we will simplify it. We'll create a new VHDL. We will call it, I don't want to copy this, I want to copy this. And we will call it MUX 221. And we will create generic. And this will allow us to define some variable that will act as a length for the STD standard logic vector. So let's create a variable n. Yeah, let's call it n. It will be integer, like this, and it will have default value of let's say 4. Here we will do std logic vector, and it will be n minus 1 down to 0. We subtract 1 because we want 4-bit, so it will be 3 down to 0, which is 4 bits. We will do the same for our output. And yeah, that's all we need to do. We can now delete all of these because we don't need them anymore. And we will look at all the code where MUX is used, and we will change it so it uses our code. Here there is no MUX, there is no MUX here, no MUX here. Let's close all of these. In part 2, we use 4-bit MUX, so we can just delete this. And since the default value is 4, we don't have to even change anything. We don't have to change anything. No MUX here, full adder. We use 1-bit. So what we will do is we will import our generic. Where is it? Here, full adder, and add our generic port. And here we will say generic map n is 1. Yes. And let's see, binary to, yes, here we have MUX, also 4 bits, so we don't need to do our generic. And I think that's all. Let's try to check for syntax errors. Okay, we got some errors. Too many actuals for block, only I think I'm not exactly sure what the error is here. Let's copy this and look at the internet. Oh yeah, I think it has to be this way. So we have to change the orientation of this arrow. Formal n does not exist. And let's look at generic. Let's look at the syntax. So we have our generic here, integer, yes, we have that. Wait, where did I edit? I don't want to edit here, I want to edit here. Okay, that's probably the error. I think now it should work. So let's look at part 5. We want to create a new Quartus project and to use switches 7 to 4 and 3 to 0 as inputs and show them on hex 5 and hex 3. Okay, let's do that now. Okay, our compilation was successful. Okay, let's begin. We will import our component number 7 segment display to part 5. Component and component, and we will create 2 instances, port map, and as input we will take switch 7 down to 4, and as output we will use hex. We will use hex 5. Hex 5. Let's copy this one more time. And this time, this will be the second instance. It'll be 3 down to 0, and we will show it on hex 3. Okay. So that's it for, did we set as a top level entity? We did. So that's it for showing the numbers, and now we will try to add these 2 numbers. And we will do it using this code. So we will create a process. Process begin and process. And we need some variables. So we will create t0 and z0, and these will be integers. So t0, t0, z0, and these will be signals. Or we can just do it like this. And it will be integer. And we can give it default value of 0. Okay. Then we need C1, and C1 will be just std logic. Is it C1 or yeah, C1 and std logic. And then we need S0 and S1. S0, S1, std logic vector 3 down to 0. So that's gonna be our BCD outputs. Now we will create our if-else statement here. Or first we will add these 2. So we will do t0 equals 2, and now we have to convert our switches, which are std logic vectors, and we have to convert them to integers, and we will do it in following way. We will say integer, then 2 unsigned, or just unsigned, I think. Yes. Or is it 2 unsigned? Let's look at the syntax. convert std logic to integer. To integer unsigned. Okay, so it's the opposite way. So here it will be to integer and here it will be just unsigned. So we will have our switch. We will have our switch from here. Then we will add one more. This time it's gonna be 0. This is gonna be 3. And the final one is our switch 8. There will be a carry in. So that's this carry in here. But we need to first, because we can't convert std logic to unsigned, so I will create a new signal. I'll create a new signal. I will call it C1 extended. And it will be std logic vector 3 down to 0. And we will say C1 extended will be just zeros with C1. And now we can do the same for our last. Can do it like this. So here we just put C1 extended. Okay, that's our addition. So we have finished line 1, and now we will do this if else. If t0 is greater than 9, then else and if. So if it's greater than z0 is equal to 10 and c1 will be 0, 0 or 1, yeah, 1, or z is going to be 0 and it's going to be. So if t0 is greater than 9, which means this is, for example, 11, then we set this to 10, which means that here we will, from 11, we will subtract 10, which gives us 1. And also this will be equal to 1, so it will be 11. If we have, for example, 4, it will be set to 0, so 4 minus 0 is 4, and here it will be set to 0, so we have 0, 4. So we will have our BCD equivalent of the binary addition. And finally, we will just assign the results. So S0, and here we want std. We want to convert the integers back to std logic vector. And unsigned. And here we will say t0 minus z0, and it will be 4 bits. So we convert these integers, or the subtraction of these integers, to unsigned of 4 bits, or std logic 4 bits. Okay, and final one, S1, will be zeros and C1. Okay, let's try to compile this if you have any errors. And then we have to show this result. So we will again copy this code. So here 2 and 3. Signal assignment statement must use to assign value to signal T0. Okay, I think we have to use this here. Okay, we have to use it everywhere. Let's see if it works now. And here we will have our S. Type conversion near text or symbol unsigned must have. Is it to unsigned? I think. Now. Yeah, seems to work. So since if we convert, unsigned and std logic vector are basically very similar in representation, but integer is different. So when we are converting from unsigned to integer, we have to use 2, and also if we are converting from integer to unsigned, we have to use 2. But here we don't have to use 2 unsigned because it's from std logic vector to unsigned. Here on the hex 1 and hex 0 we will show the results, and we want to hex 0 will be S0 and hex 1 will be S1. Okay, let's try to compile. Use the Quartus okay, must contain sensitive list. Okay, we'll every time switches change, we will call this code. Yeah, seems to work. Use the Quartus RTL viewer tool to examine the circuit produced by compiling your VHDL code. Compare the circuit to the one you designed in part 4. Okay, we'll do it after we finish compilation. And then we will look at part 6. Okay, so we can program. So as you can see, we have our hex numbers and they are showing. Why is there 8? Wait, there's some mistake made. Hex 5 switches. Okay, there was just a faulty switch. So now you can see that we have all zeros, and we can add these two numbers and show them on the display here. So for example, we have 1 here and 1 here, and we can see that 1 plus 1 is 2. We can do 9 plus 1, that's 11. Okay. That's not correct, but I think let's okay, there is some error in our code, so we have to look at it. C1 shows correct. This is village method unsigned. set 0. Here we extend. Oh, I see. I think this should be... This should not be C1. I think this should be switch 8. That's our... And this is supposed to be C0 extended, not... Okay. This is C0, not C1. Now it should be correct. I want to keep these videos shorter, so I think we will finish part 5 today, and we will look at part 6 in the next video. Let's wait for this to compile. And we'll program this. And now it should work as expected. So we have 1 plus 1 is 2, plus 9 is 10, yes. 9 plus 9 is 18, and we can add our carry in. So 9 plus 9 plus 1 is 19. We can do, for example, let's do, this is a number greater than 9, so we show just dash. And we will want to see 7 plus, for example, 5. So let's show 5 here. No, not this one. This one. So 7 plus 5 is 12. That's correct. We can add our carry in. So this design seems to work correctly. Great. And we will also look at the RTL viewer to see how this design is implemented. Okay. So we have our 7-segment displays here. Then we have 1 adder, 2 adders. We have comparator and another adder. Okay, let's zoom in a little bit. Okay, not like that. And this is adding our 2 numbers. And then the yeah, this is our comparator. We have our comparator. If you look at part 4, or the design here, okay, we can't look at it, but we have our adder here, and we add well, yeah, I can't really see what it does here. Yeah. But anyway, we have finished today's project, part 5. This was our code. And I think that's it for part 5. Yes. And next time we'll look at part 6, which is converting 6-bit binary number into a 2-digit decimal number. So instead of adding two numbers and showing them, we will just show a 6-bit binary number, since now we are showing 4-bit binary number. That's it for this part. If you want to see part 6, don't forget to subscribe, and I'll see you in the next one. Bye.